Welcome. On this video, we will talk about the partial sum of geometric and arithmetic sequence. So let's start by discussing the small introduction question, which states, let's take in consideration two types of sequences. A of n is going to be an infinite arithmetic sequence, and B of n is going to be an infinite geometric sequence. For A, what we want to do here is we want to find the partial sum of the fifth partial sum of the arithmetic sequence. So for A, we just want to concentrate on A of n, because A of n is the explicit formula for the infinite arithmetic sequence. So remember that the fifth partial sum, this is equivalent to just finding the sum from the first to the fifth term of the given sequence, which in this case, the sequence is defined as 2 plus n minus 1 times 3. So all we got to do is just going to plug in our values for n all the way from 1 to 5, given the expression that represents this sequence. So let's do that. So to find the first term, all we got to do is just plug in n for 1. And notice that this expression now is going to give us the first term. So now let's find the second term. To find the second term in the sequence, all we got to do is go to our equation. And now let's plug in our value for 2. So this expression is going to be equivalent to the value of the second term. So now let's find the third one. And again, this expression that we just found here, this is going to be the expression for the third term. So now let's find the fourth term. So now that's going to be of 2 plus now 4 minus 1, since we're looking at the fourth term. So now this is the expression for the fourth term. And let's just find the fifth term now. And now this expression is going to give us the value of the fifth term. So if we want to find the fifth partial sum, all we got to do is just add up those results. So let's actually find out the value. So 1 minus 1, that's 0, times 3, that's 0, and 0 plus 2, well, that's 2. So that's the value of the first term. Now let's simplify the second one. 2 minus 1, that's 1 times 3. So that's 3 plus 2, that's 5. 3 minus 1, that's 2. 2 times 3 is 6. 6 and 2, that's 8. We stated that this is the fourth term, so which one are we on? We're in the fourth term. So 4 minus 1, that's 3. 3 times 3, that's 9. 9 and 2, that's 11. And lastly, the fifth term, 5 minus 1, that's 4. 4 times 3, that's 12. 12 and 2, that's 14. So if we add all our results, this is going to be equivalent to just 40. So if we would have added the first 5 terms on the sequence, we would have got a result of 40. So at least this completes exercise A. So now what we want to do in exercise B is the following. Well, now let's take in consideration this expression, n over 2 parentheses first term plus a nth term. And now what we want to do is let's compute this expression assigning the value of n equals to 5. What do we notice? Well, at least for B, let's take in consideration the expression n over 2 of a1 plus an. And now, if we let n to be equals to 5, let's plug that in. So now we're going to have the expression of 5 over 2. A1 is the first term, which we already know that is 2, plus an, so we're looking at the fifth term, which we can definitely simplify this, and now this becomes 5 over 2, 2 plus, and the fifth term in my sequence, so that's 1, 2, 3, 4, 5, that was the fifth term on the sequence, which is 14. And now if we simplify this, we got 16. And if we simplify all this, well, 16 over 2, that's 8. So now we got 5 over 8, which is equivalent to 40. And what do we notice? Well, what we should have noticed is that this result is equivalent to example A. But why is it that this expression right here gave us the same result as just finding the the fifth partial sum on the sequence? That's going to be our lesson for today. How come this expression can give us the same result as just finding the fifth term in the sequence? Because notice that here we're using n to be equals to 5. So therefore, our result should be equivalent to the fifth term. But what's the relationship between this expression that we do have here and the actual result that we got in A? But that's the actual lesson for today. But this at least when we talk about an arithmetic sequence. Well, let's see now, because now on the next problem it says, let's find the partial sum of the geometric sequence. Well, recall that the geometric sequence, it was our b of n, which recall that b of n is defined as just 4 times 2 of n minus 1. Okay. So now let's see, what do we want to do with this now? Well, let's find the partial sum, the fourth partial sum of the sequence defined by this explicit. So if we want to find s of 4, well, that's equivalent to just adding the first 4 terms in this sequence. 4 of 2 and minus 1. So let's do that. Let's find the first 4 terms and let's add their values. So for that, we're going to get, so for the first term, we're going to get the following. So let's assign n to be equivalent to 1. So this is going to be my first term. Let's find the second term. So 4 plus 2, and let's assign n to be equivalent to 2. So we got minus 1 now. So this is going to be the expression for the second term. So now let's find the third term, 4 times 2, and now let's assign n to be of 3. So this is the expression for the third term. And lastly, since we want to find the fourth partial sum, then we're going to find the value of the fourth term. So let's assign n to be equals to 4. And again, this is the expression that will represent the fourth term. So let's see. Let's add them up and let's see what we get here. Well, 1 minus 1 is 0. 2 to the 0, that's 1. 1 times 4 is 4. Now for the second term. So now my second term, 2 minus 1, that's 1. 2 to the first, that's 2. And 2 times 4, that's 8. Let's find the third term. Exponent is 2. So 2 to the second, that's 4. And 4 times 4 is 16. Now, lastly, the fourth term, we got 4 minus 1, that's 3. So 2 to the third times 4, well, that's going to be equivalent to 32. So if we add the first 4 terms in the sequence, we're going to get a result of 60. So at least we already found the fourth partial sum for this geometric sequence. But now, let's take in consideration this new expression right here. And now let's assign the value of n to be equals to 4 to this expression. And let's see, is there any relationship between the results on D and C? Well, let's see, the expression that I want to be using is 1 minus r of n over 1 minus r. And now if we assign n to be equals to 4, well, let's plug that in. So we're going to get the fourth term. So I'm sorry, this is a of 1, so that doesn't change. So the first value, or the first term in my sequence, was a value of 4. So there it is, 1 minus r. But notice that for this r, we want to use the common ratio that is given to us in the sequence. So if the first term is 4, the second is 8, the third is 16, and the fourth is 32. So that just implies that My common ratio is 2, so therefore for r, I'm going to plug in 2. For n, I'm using the value of 4 over 1 minus 2. And let's see what does this result give me. And if we simplify this, we're going to get 4, 1 minus 16 over, well, 1 minus 2, that's negative 1. So let's continue simplifying this. We're just going to get minus 15 over minus 1. So this is equivalent to 4 times 15, which this is also equivalent to 60. So what relationship do we notice here? Well, we can see that C and D have the same result. So therefore, perhaps we can use this formula to properly identify the partial sum of a geometric sequence. But how come this expression gives us the same result as the fourth partial sum? Well, in this case, it's because we're using the same value of n. So if we want to find the fifth partial sum, then we would assign n equals to 5. But regardless of the values of 5, this expression will always give us the result of the partial sum of a geometric sequence. And if your sequence is being defined as arithmetic, then we can use this expression to define the partial sum of an arithmetic sequence. So now the most important question is, why is it that this equation gives us the same result? Well, that's the actual lesson for today. So why do the partial sum of those formulas that we just worked on actually work on? Well, first, let's take in consideration the partial sum of an arithmetic sequence. Right now, we're stating that the partial sum of an arithmetic sequence, it can be defined by this expression, a of 1 plus a of n. And this is something to memorize. The partial sum of any arithmetic sequence can be defined this way: n over 2, parentheses, first term plus the nth term. And this will always give you the same result as just adding the first nth terms in the sequence. But why is this true? Well, s of n represents the sum of the first n term. So let's define it as adding the first term plus adding the second term, which notice that the second term can be defined as this: just the first term plus a difference. And we should have added the next term, which is the third term, which knows that the next term, or the third term, can be defined as just, I'm sorry, this is a 3. Then we need to add the next term. So we need to add the fourth term, but notice that we can use this expression to define the fourth term. And since we want to find the s of n, or the nth partial sum, so we're just going to add a bunch of other terms until we reach to the second to last term, which the expression that I'm going to use is n minus 2 times d. So this will be equivalent to the an minus 1 term. And lastly, the nth term can be defined as just n minus 1 times d, which again, notice that this is the explicit formula that we discussed previously for the arithmetic sequence. So all we have said is, look, if I want to find the ninth partial sum, then I need to add all terms up to n. And all we have done, we have just wrote down a single expression for every single one of them. Well, let me define this as s of n, and we already did. But notice that now I'm going to rewrite s of n. And now I'm going to rewrite s of n, but since every single term is being added, then it doesn't really matter the order. So I'm just going to list them in decreasing order. So I'm going to write them out. First, the n term. So this is going to represent the n term. And then I'm going to add the second to last term. Then I'm going to add up the next term. So that'll be a1 plus n minus 3 times d. So this would be the second to last term. And we're going to continue adding all that until we reach to the second term. And again, this is the second term. And the first term, where the first term is just itself. Now that we have defined the partial sum in two ways, well, first in increasing order and then in decreasing order, what I'm going to say is, well, since I have two expressions that are equivalent to s of n, well, let me add it up. Well, let me say that I have 2s of n. Well, what is 2s of n equivalent to? Well, if this is s of n, and it's all made out of a different term, and this is s of n as well, and it's composed of a lot of terms as well, then 2s of n is just the addition of all the terms in both expressions here. So if I want to add them up, I'm just going to add them up in order. So I'm going to add the first term of my first expression for s of n with the first term in the second expression of s of n. And if I add them too, because again, right now I'm trying to define 2s of n, which is just the addition of those two. But if I add them up, notice what this is going to give me. So it's going to be a plus a, so that's 2 a's of 1 plus this expression, n minus 1 times d. So therefore, all I'm doing, I'm just going to add all the terms in the sequence. So I'm going to add the second term in the first s of n with the second term. And what is this going to give us? Well, so a first times a first, well, that's still equivalent to 2 a's of 1. But now this next expression is going to be a little bit confusing. So let me just do it here on the side. So now we're going to have d plus n minus 2 times d. Again, right now I'm just adding d with the second expression here. Well, let's see if we can simplify this. Well, this is equivalent to d plus n of d minus 2d. We can combine the d's in here. So now we have n of d minus d, which again, this is just equivalent to just d of n minus 1, or n minus 1 times d. So notice that we still have the same expression here. So it will be 2a plus n minus 1 times d. And then we're going to move forward and we're going to add the next term. So the third term of s of n with the third term of the second s of n. And if I add them up, you can verify this, but this is still going to give us 2 a's of 1 plus n minus 1 times d. And then we're going to just say, well, there's going to be a bunch of addition on them. And now if I add the second to last term here, if I add this 2 here, you will see that we still have the same expression, 2a plus 1 times n minus 1 times d. And if I add the last terms in here, we still should get the same expression. So we're still going to get the same expression of 2 a's of 1 plus n minus 1 times d. So all we have done, we have add up a lot of terms. So let's see if we can simplify this. Well, one thing to notice is that we have a lot of terms. Oops, all the way up to here, sorry. All the terms in the sequence are the same expression now. And how many of them we have? Well, we have n terms, because there were n values that we needed to add up, and every single term has the same expression. So now we have n terms with the same expression. So now perhaps at this point, we can rewrite the expression 2 of s of n. That's equivalent to n of those expressions. But notice that this expression, it's only going to give us a result of 2s of n, but we only wanted s of n. So perhaps we needed to divide both sides for n. So now we have that s of n is equivalent to n minus 2, and now we have this big expression, 2 a's of 1 plus n minus 1 times d. And the last thing that we got to do here is now, let's just try to rewrite what's inside the parentheses. So let's just do a small calculation here on the side. So 2a1 plus n minus 1 times z. Well, 2 of a of 1 is a1 plus a1. And now let's just rewrite what we have here on the right-hand side. Plus n minus 1 times z. But now notice that this is just equivalent to a1. And now this expression right here, this is the same expression that we use to define the nth term in the explicit formula that we have discussed previously. So now, after doing all this manipulation, we can say that S of n is equivalent to n over 2. And on the inside, we're going to have a first plus a of n. And what we have shown is that regardless of how many terms we have, the partial sum of the first n terms in any arithmetic sequence, it's always going to be equivalent to this expression, which is what we define in here, and which is what we use here to show that we got the first, the sum of the first 5 terms. That covers arithmetic sequence. So this is just a very heavily algebraic manipulation just to show that if you add the first n terms, then that's equivalent to this. And this only works for arithmetic sequence. But we also discussed that if we have a geometric sequence, we can define the partial sum as a1. Well, let me change the color to be a1 times 1 minus Rn over 1 minus R. So to find the partial sum of the first n terms in a geometric sequence, we can use this expression right here. But now the most interesting question is, how come? How come this is true? If I add the first n terms in the sequence, it's equivalent to just this expression. Well, let's show that. Let's write down an expression for the first partial sum. So S of n is going to be equivalent to the first term plus the second term, but since this is a geometric sequence, the second term can be equivalent to a first times r plus the third term, but now the third term is equivalent to a1 times r to the second plus the next term, which is a fourth term, but notice that the fourth term can also be defined as a1 plus r to the third, plus the fifth term, which the fifth term is r to the fourth. And we can continue doing all this until we reach to the nth term. And we have discussed previously that the nth term it's equivalent to the explicit equation that we have defined previously. So notice that this is essentially the same idea as we did in arithmetic sequence. We said, look, if I want to find the nth partial sum, then I need to add the first nth terms. And what we have done here is just write down one expression that will cover all nth terms in the sequence. And what we want to do now is we want to manipulate all this. So what I'm going to say is, well, if this is the expression that we can use to find the sum of the first n terms, then what is equivalent to r S of n? What if I get every single term and I multiply by r? Well, if I get every single term and I multiply by r, then now my first term becomes a1 times r. And now my second term becomes a1 times r to the second. Well, I shouldn't call it second term. It's not really the second term, just a manipulation of the second term. And now my third term will become a1 times r to the third. And now my fourth term. So notice that all we're doing, I'm just increasing the exponent of r by 1. So now my next term is r to the fifth. And now the last term is going to be a1 times r to the n. And again, all we have done, we have just taken every single term and just multiplied by r. And let me just show what expression is for what term. Okay, so this expression is for the first term multiplied by r, second term multiplied by r, third, fourth, fifth, and the nth one. So now that I have an expression for s of n and r s of n, let me just manipulate this a little bit and say, well, what would have happened if I were to subtract them? So what would have happened if I get all the terms defined in s of n and I subtract the terms defined by r s of n? So what would have happened with those two? Well, what would have happened here is a lot of terms are going to cancel out. Because now, if I get the top and I subtract the bottom, you can think of all the expressions here on the bottom are negative, and therefore this term will cancel out with this expression. This expression will cancel out with this expression. This expression will cancel out with this expression. This expression will cancel out with this expression. The next expression should cancel out with arrow fifth. And now a1r minus 1 should cancel out with the second to last expression. And all that is going to be left is the first term plus the last term. So now we have an expression. It's a very weird one, but at least this expression is using the s of n. And since I want to have an expression for s of n, then notice that here on the left-hand side, we got two terms, two big terms that uses both the expression of s of n. So let's factor out of s of n. And now we're going to have 1 minus r equals a1 plus a1 r of n. Since I do want to have an expression for s of n, so I'm going to divide both sides by 1 minus r. And I notice that after doing all this manipulation, I finally have an expression for s of n, where s of n is equivalent to a1 plus a1 rn all over 1 minus r. Which we can still simplify this, because notice that on the top, we still have a of n. So now we have a of 1, parenthesis, 1 minus r of n, all over 1 minus r. And what we have said is this. We can use this expression to properly define the partial sum of the first n terms, given that the sequence is a geometric sequence. And this is a very powerful tool to have or to understand, because now imagine that you want to find the 30th partial sum. What you can do is find all 30th terms and add them up, and you will get your result. Or if you know that it's a geometric sequence, all you got to do is plug in n for 30th, define a1, define r, and now this expression is going to give you that same result. And the same for an arithmetic sequence. Let's say you want to find the nth, the 40th partial sum. You got two options there. Either you can find the first 40th terms and then add them up at the end, or you can just use this equation here. If you know that it's an arithmetic sequence, you plug in the value of n, you plug in the first term, the 40th term, which you can find using the explicit formula that we discussed previously, and you will get the same result, just like we did here. To find now, this should make a little more sense, because now we got two ways. Either we can add all the terms that we wanted, or we can just use the formula and we will get the same result. So this is the expression that we'll be using for an arithmetic sequence. And this is the expression that we'll be using for a geometric sequence.